Good afternoon, everyone. This is Alan. Today, we're going to review the things we have learned last week. The first thing is inner product. This is a concept directly generalized from vector space. So let's review that in vector space. If we have two vector A equals to A1, A2, A3 in 3 dimension respectively, and a vector B equals to B1, B2, and B3 in 3 dimension respectively, and then their inner product, or denoted in this way, is defined as A1 times B1 plus A2 plus B2 plus A3 times B3. And now, in functional space, we can define the inner product similarly. If f and g are functions on interval a, b, then their inner product is defined as the integral of the product of these two functions. With this, we can define more concepts. First is orthogonality. In vector space, if we have two vector orthogonal, we mean that their inner product is 0. I'll write it in this way. So orthogonality is equivalent with inner product equals to 0. Since we have defined inner product in function space, we can also define orthogonality in functional space. Here, I have some remarks. So when we define orthogonality, we used the definition of inner product, and the inner product is an integral, and that integral have a domain, which is a domain of the function. And in the definition of orthogonality, I would like to mention that the domain matters. Let's look at a simple example. The inner product of x and x squared on the interval -1 to 1 equals to the integral from -1 to 1 of x times x squared, which is the integral from -1 to 1 of x to the power of 3, and that equals to 0. That means on interval -1 to 1, function x and the function x squared are orthogonal with each other. But if we define this inner product on other interval, like on interval 1, 2, then the inner product becomes integral from 1 to 2 of x times x squared dx equals to integral from 1 to 2 x to the power of 3 equals to 15/4, which is not 0. That means on interval 1 to 2, x is not orthogonal to x squared. Next, let's look at norm and normalization. In vector space, vector A defined as A1, A2, A3 in 3 dimensions respectively, and the length of vector A can be defined as the square root of the sum of square of each dimension. So it's the square root of A1 squared plus A2 squared plus A3 squared, which is also the square root of the inner product between A and itself. Beyond this, we can also define the unit vector, which is the vector of length 1. For any vector A, we can define a vector E that is 1 over the norm of A times A. The property of E is that E and A point to the same direction, and E have the norm 1. In function space, things are similar. Since in function space we have previously defined inner product, we can similarly define the length of the function, or in this case we call the norm of the function to be the square root of the inner product of f between itself, which is the square root of integral from a to b of f squared, and the normalization of f is f tilde equals to 1 over the norm of f times f. And the good property of f tilde is the norm of it equals to 1. The last concept we need to know is complete set. So in 3D vector space, if we have a set consists of E1, E2, E3, which is E1 equals to 1, 0, 0, and E2 equals to 0, 1, 0. E3 equals to 0, 0, 1. If we have such a set, then we can say for any vector in this vector space, like A equals to A1, A2, A3, we can write A as a linear combination of these 3 vectors, like this. A equals to A1 times E1 plus A2 times E2 plus A3 times E3. For example, such a vector 1.5, 3.3 minus 1 can be written as 1.5 times E1 plus 3.3 times E2 plus minus 1 times E3. So for any vector in this space, it can be represented as a linear combination of such a set. Then we say such a set is a complete set. In function space, we have similar result, but things are a little bit different because function have domain like on which it is defined. For example, if we have a function fx, it is defined on minus pi to pi. We have previously learned that we can expand it as Fourier series, which is fx equals to a naught plus a summation from 1 to infinite of an times sine nx plus bn times cosine nx. And that means such a set consists of 1 cosine nx with different n, sine nx with different n, consists of a complete set for function defined on minus pi to pi. And in this section, the textbook introduced a theorem which is given without proof that for any function fx defined on minus 1 to 1, it can be expanded as a Legendre theorem. And the Legendre series is like this. Fx equals to the summation from 0 to infinite. An is a coefficient times Pn is the unnormalized Legendre polynomial, which is the same as the other form, which is the summation from 0 to infinite of an star times Pn. The lowercase pn represent normalized Legendre polynomial, and a star equals to an times the norm of the unnormalized Legendre polynomial. So the coefficient of these two representation are different by a norm of unnormalized Legendre polynomial. That is all for today. Thank you.